Thank you for being here. It's a pleasure to host this WISE public lecture. My name is Claudio Canizares. I'm the Executive Director and Professor of Electrical and Computer Engineering here in this building. And I'm an Executive Director of the Waterloo Institute for Sustainable Energy, WISE, which is sponsoring this presentation. Thank you to our guest, Nelson Leite, which I'll be introducing shortly. Before I do that, I would like to make a territorial acknowledgement. The University of Waterloo acknowledges that much of our work takes place in the traditional territory of the Neutral, Anishinaabe, and Haudenosaunee people. Our main campus is situated on the Haldimand Tract, the land granted to the Six Nations that includes 6 miles of each side of the Grand River. Our active work toward reconciliation takes place across our campuses through research, learning, teaching, and community building, and is centralized within the Office of Indigenous Relations. In fact, WISE has an initiative. We have a program led by Ambika Opo, which is sitting here, dealing with all these issues of access to energy, affordable energy for humanity, AE4H, and we have a lot of interactions with remote communities, indigenous communities. In fact, we are part of a project in which Nelson's company is involved in precisely deploying some equipment in some of these communities. Let me introduce our guest, Nelson Leite. Chief Operating Officer, is focused on the design, development, and production of the FuelPositive prototype units of the future commercialized units. Nelson comes from an engineering and manufacturing background with over 30 years in the high-tech automation and robotics industries. His key transferable experiences include inventing solutions for companies such as Toyota, Tesla, Kimberly-Clark, and many more. The size of systems range from smaller, under 100,000, to large projects over 10 million. Many of the systems are currently in production today at the various facilities around the world. At FuelPositive, Nelson is taking an aggressive approach, driving the commercialization of our systems, along with evolving the technology further with our team of researchers and scientists. Nelson is going to be introducing us to the work that been done at FuelPositive. We have been interacting with Nelson and his company now for a little while. We appreciate your acceptance of the invitation, and welcome to Waterloo and WISE, and look forward to your presentation. The floor is yours. Thank you, Nelson.
Thank you so much. Good afternoon, everyone, and thanks for taking the time and having me as a guest speaker here for this lecture. The lecture is titled Containerized Green Ammonia Systems, Prioritizing Farmers and Food Security. I hope you're going to find this very informative. We'll have plenty of time after for some questions, and maybe even some time for some answers too. And thanks for spending Valentine's Day with me. There's a little Snoopy, so thank you so much. This is our formal disclaimer. We are a public company, so it's important that I do display this. I won't have you read it all because I'm not that mean, but it will be published, and I think we're recording this for YouTube as well. So I guess if you're watching this in the future, hopefully it's not because I'm no longer with us, but I hope that everybody finds this very informative. We also have our land acknowledgement as well, and we'll move on to our agenda. We're going to do some introductions because there's some team members that have contributed to this lecture as well that I want to introduce. Background on FuelPositive. We'll refer to FuelPositive many times as FP. We're going to talk a little bit about ammonia, our system, and a case study in particular for a remote community. Myself, I'm Nelson Leite. It can be pronounced many ways, but Leite is pretty good as well. Thanks, Claudio. We're focused on the design, development, and production. Come from over 30 years of background. I am a member of the American Institute for Chemical Engineering and for Center for Hydrogen Safety, as well as the Ammonia Energy Association. I am committed to the safe and innovative production of distributed hydrogen and ammonia systems. I was born and raised here in Kitchener-Waterloo area, in a small house with many family members, like two bedrooms and 4 older brothers. So I actually didn't sleep alone until I was married. But I continue to support the local institutions developing clean technologies for agriculture. My son actually just graduated from Waterloo last spring, and he's left us for Arkansas. So he won't be taking part in much of our what we're doing at Fuel Positive. So we're just going to skip through here. Francisco, we call him Paco, by his choice. He likes that name. Paco Mora, he's a chemical engineering technician. He's got his Master's of Science from University of Mexico. Forgive me, I'm just paging through some of my slides here. Francisco holds a Master's of Science in Chemical Engineering from Mexico and continues to develop and optimize our green ammonia synthesis technologies. He will be focusing in on working with the university for catalyst development in the future and also electrolysis development. Sydney Collette, who's our R&D Center administrative professional from Waterloo here, heavily involved in the administration of our safety protocols, including anhydrous ammonia, ammonia best practices, transportation of dangerous goods, compressed gas safety, along with many others. Remy, you see here, is her sidekick and greeter. We're animal lovers as a whole, and we are a pet-friendly environment. We have not had my cat Eddie and Remy together in the same room yet, but I'm sure that's going to happen sometime. Then lastly, we have Nicholas Hibania. He's an intern from Laurier working on research and data analytics. We fully support the co-op programs with 4 individuals currently working at our location in Waterloo, all from the local universities and colleges for this semester. We do believe in planting the seeds and nurturing growth in our youth, and we look to our universities for many of our resources moving forward. So now let's get to the heart of the presentation and talk about who Fuel Positive is and what we're doing. As a brief introduction, we are a company dedicated to acquiring and bringing clean, sustainable, and economically viable environmental solutions that can be deployed in a short term, not decades from now. The key being sustainable and economically viable. Our initial technology is a system for producing green ammonia. We are now in the pilot demonstration phase in TRL 7, working quickly to completing TRL 8. Our systems are designed to produce green ammonia on site for a wide variety of uses, especially carbon-free fertilizers and fuel. Although our systems may be considered small, the impact can make a difference one farm at a time. Our team is located throughout North America with members in Calgary, Toronto, Montreal, Nova Scotia, and in the United States and Carolina. Our facilities are located in Waterloo, with our manufacturing and R&D center on Northland Drive, and our headquarters and sales is located on Weber Street. Our plan is to expand to a large parcel of land on the outskirts of Waterloo, where the plan is to build a phased out building that will take us to 140,000 square feet. In addition to this, we have access to over 100 acres of rural land where we will be setting up a test site to mimic off-grid applications and develop application methods for the products that we produce. Some examples will be off-grid anhydrous ammonia, optional hydrogen pumping station, and aqua ammonia takeoff modules, an ammonia burning grain drying system, and hopefully hydrogen and ammonia fuel cell tractors. We will also develop more modern storage systems and safer transfer equipment for farmers when they are filling their own systems. On this test site, we'll also be able to develop our system for controlled environment farming or greenhouses and develop new technologies to minimize nitrogen loss, such as ammonia inhibitors for fall application. You can also see our mass spec unit, which will travel to the pilot sites in our portable lab. Hopefully I'm not going too quickly. It's a lot of slides to get through. And maybe if somebody can give me a warning when we're getting close to the time, because I can speak through some of them. Okay. Our growth, the growth of our technology and the development of our new technologies wouldn't be possible without working as a team with others. For example, our presence here today stemmed from relationships we built over the years with the University of Waterloo and our more recent involvement with WISE. We also work with other institutions and partner up on technologies that will create positive impact on the environment. Here are a few of our partners in our quest for developing carbon-free solutions. In addition to this, we have supplier partnerships throughout the world, shown on this map of Canada. But prior to getting into the partners around the world, here you'll see that we also work with Laurier, University of Guelph, but Waterloo is very close, near and dear to us, as well as WISE now. Claudio has really endeared himself to us. Let's move on. So what is ammonia? I'm sure most of you here in the room know what ammonia is. We've been using it as a chemical for over 100 years. Today, over 200 million tons of ammonia is consumed worldwide and is expected to increase drastically. Let's compare that to other gases such as propane. 175 million tons of propane is used in the world compared to 200 million tons of ammonia. We're expecting ammonia demand to triple in the next little while, and we'll talk a little bit about why. Ammonia is used in a number of other crucial manufacturing processes in these smaller yet substantial markets, but also benefit greatly from FuelPositive's carbon-free ammonia solutions. Since ammonia is more easily stored and transported than hydrogen, it is being considered as a carrier for hydrogen. And we're hearing a lot about that on a daily basis, as I'm sure you are as well. So reasons why ammonia demand is growing. Rapid growing demand for food, therefore an increased demand for ammonia. Food demand is expected to rise by 28% according to Agriculture Canada, far outpacing our ability to supply, which is currently pegged at approximately 8% growth. The attention to green ammonia is slowing down. There you see actually one of our farmers applying anhydrous ammonia on their field in Manitoba. The attention to green ammonia is slowing down. The current growth and investment of traditional ammonia. So if you're a company that has the traditional ammonia plant and the demand is growing, normally you would think to expand those facilities. But because of the attention put on green ammonia and the carbon emissions and the environment, they're redirecting those investments into green ammonia plants. So that is good news, but temporarily slowing down the growth, the production of ammonia. The maritime industries is rapidly expanding its use of ammonia as a fuel. And here you see this is a tanker that is slated to start being used next year. And it runs on green ammonia. And you'll see in some other charts how much growth the ammonia market in maritimes is, what we're seeing for the growth and the trajectory there. The aviation industry is using green ammonia as a jet fuel, and we're already seeing that actually come to market. And the power industry is converting green ammonia for power. And here I think it's a Mitsubishi turbine running on green ammonia. And obviously using ammonia for a hydrogen carrier as well. And there you see a hydrogen, an ammonia cracker. So here you see a chart that shows the demand scenarios, short-term, medium, long-term. This is put together by Argus Media through the Ammonia Energy Association. And what it illustrates is from left to right, 2020 to 2030 on the chart on the left. And on the chart on the right, 2030 to 2050. The key points here are marine fuels, H2 carrier, and power generation lead the charge for the demand. We don't really see a big charge in agriculture. And we'll get to some of that a little bit later. Agriculture is actually expected to be the lower priority in the supply chain. So that provides additional opportunity for our systems and many other systems. So we look at some of the other analyst predictions on the ammonia market. And if we, what we're seeing from one analyst is the CAGR, which is a compounded annual growth rate, is around 75% between up to 2030, which is significant. And to corroborate this, we also compare it with 3 others, which were corroborating this data. We're seeing research from Precedence Research, from Markets and Markets, and from FMI. This is good news because this is the green ammonia. So what we're seeing is the market of normal ammonia, which is heavily carbon emitting, is transferring over to green ammonia, and companies are changing the way they're looking at it. So much so that if you look at the bottom graph, and if we look at the FMI curve, which is the blue one on the right, it states $6.27 billion US in ammonia market. The market itself is probably over 200 billion. So this is what they predict would happen by 2030. Now, but what we did was we looked at the updated numbers, which recently came out, and the same research firm predicts now 17.9 billion in the same time frame. So what took place in the last little bit? Obviously, they're seeing what's happening in the industry, and they're seeing that there's a real need for green ammonia. And what they're doing is changing their investments in the future. Instead of making conventional ammonia to making green ammonia. So it's terrific news. So it's very, very uplifting when you're in the industry. Here's a slide to show you how the traditional ammonia manufacturing system works and the pollution it causes. The first thing you see in the far left shows that coal, naphtha, or natural gas are used to power these massive ammonia refineries. These alone cause huge greenhouse gas emissions. In fact, a global average of almost 4 tons of greenhouse gas emissions are emitted for every 1 ton of ammonia produced. Imagine that, four times. And thank the heavens that we're switching over to green ammonia. After it's produced, the ammonia is stored near the refinery before it's being transported to ships, trains, transport trucks, or pipelines to get to the next holding station along the way. That's when all the supply chain problems kick in. So you can see how we just compound on the greenhouse gas emissions throughout the chain. So without ammonia, our crop yields are reduced. This chart can show how the crop yields have grown over the years. So this is based on 1 acre of farmland. Not all farmland is the same. So if we look at Manitoba, it's very fertile farmland. If you look at Ireland, it's not so much, but it has its good areas. But if you start to apply fertilizer along with some best farming practices, you start to increase your crop yields. So according to Agriculture Canada, again, 28% growth in the food demand, and we can only keep up to 8% growth if we continue to do what we're doing right now. That's fertilizing. But there's a big push for reduced nitrogen emissions. And initially, beginning of last year, the Canadian government rolled out a program to ban all nitrogen fertilizers. They very quickly reassessed that and reflected on those numbers with Fertilizer Canada, and came back and changed their approach to listening to the farmers and see, well, how can we continue to increase our yields or keep our yields the same and reduce the nitrogen emissions with still getting the benefits of reducing emissions, reducing greenhouse gases, et cetera, but without banning everything. This does show that you get 120 bushels per acre back in 1993, where they were using very limited use of anhydrous ammonia and other forms of best practices in farming, up until 180 bushels in 2021. And this is the average. people get over 220 bushels of corn per acre. But just imagine if you said stop using fertilizer and you go back down to roughly 100 to 110 bushels. So what's that going to do on our food supply? That's one of the reasons why you start seeing food prices go up. And that's in Canada, where we have great access, I believe, to our food. But imagine if you're in a third world country, in our country that doesn't have the access, it just gets worse. So we really have to work together to see if we can solve this. I think we're doing it. We believe we're helping to do it and help to bring some attention to it, and so are many others. This graph here shows the cost of ammonia now over the last few years, increasing to over $1,600 US per ton. FCC and Argus Media are forecasting prices to remain north of the $1,500 USD mark, which is over $2,000 Canadian, which was confirmed this week again. But if you look back in January of 2000, it was roughly $250 a ton. So the cost keeps going up, and it makes sense, because if an agricultural ammonia provider can get more money for the ammonia from another market, they will. It's been costing, I know it costs you a lot more to get to school. I'm sure your tuitions have gone up. So it's costing everybody more to do anything. So the cost of anhydrous does keep going up. So what do we know so far at this presentation? Almost 4 tons of GHG emissions per ton of ammonia produced. Ammonia market will be over 400 million tons by 2030. Demand continues to outgrow our pace. Crop yields rely on ammonia, and ammonia prices are over $2,000 Canadian per ton. We usually get into it a little bit more, but we're going to get right to our system. So, however, with all these problems, FuelPositive's technology will help solve a portion of the demand, the emissions, and the price. It decentralizes and decarbonizes ammonia production, and it changes how ammonia is manufactured, distributed, and consumed. Our patent-pending production system includes a nitrogen generator to produce the nitrogen from the air, a water electrolyzer to produce hydrogen from the water, and a novel patent-pending ammonia synthesis reactor or converter system to produce green ammonia by combining the two. Our system utilizes sustainable electricity such as solar, wind, or hydro energy, and the resultant green ammonia is stored in a pressurized tank under the same pressure as propane. Farmers typically apply ammonia in their fields twice a year, in spring and fall, and some in early summer. So our system stores a minimum of 6 months worth of green ammonia production. Our containerized systems are modular and scalable. They're built to fit within 20-foot and 40-foot shipping containers. That means that they can be easily transported directly to the farm where the green ammonia is needed. And our output can be scaled up or down depending on the user's requirements. So one of our systems supplies roughly 100 tons of ammonia per year and can be stacked up. 100 tons, you might wonder, well, what does that do? What can that supply? And that generally will supply a farm of about 1,200 to 1,500 acres. In Ontario, I know when you're driving on the 401, you're looking at the farms, and if you look what's considered a big farm in Ontario, is typically about 350 acres. In Manitoba, a big farm is like 12,000 acres. So they go through a lot of anhydrous. Well, they go through a lot of fertilizer, period. Not all of them are using anhydrous. Anhydrous is specialized, so it is dangerous to use. And one of the reasons why we don't use it too much in Ontario, the regulations are very strict here in Ontario, which is similar to Europe. And so you heard me mention the aqueous module, which is kind of like a diluted form of anhydrous, much safer to use. But it does have its disadvantages too. It's much heavier, so soil compaction takes a lot longer to apply. So if you're a farmer with 14,000 acres and your kids have all gone away and moved away, and you have to apply fertilizer to all these different fields, and with anhydrous, you can do it in one pass. And with aqueous, you have to take 5 or 6 or 7 passes. You don't have much time. You might opt to go with anhydrous. So you have to think about all that. Soil compaction as well. You're carrying this huge water tank and you're squishing down the soil. It's like out in your garden, you've planted your seeds and then you walk over top of it. So some of the things that normally we don't consider. The GHG emissions reductions are pretty significant. Subsequent rollout of our technologies will help Canada meet its 2030 and 2050 objectives regarding emissions reductions projections, and specifically will immediately reduce on-farm emissions. This slide does show how our system reduces emissions over time, following a realistic production schedule. Each system manufactured by FuelPositive will produce 300 kilograms per day of green ammonia, or 100 metric tons per year, reducing GHG emissions by 181 tons CO2e in Canada, or 287 tons of CO2e using worldwide ammonia production numbers. We expect our system will be able to do more than this. Each system has a long operational life measured in decades and will require minimal maintenance. We are expecting the systems to run at least 30 years, which is a very long time. Applying a conservative model, we expect that by year 20, the combination of all fuel-positive systems in the field will collectively reduce GHG emissions by over 4.6 million tons of CO2e annually. And on one of those first slides, we talked about doing it one farm at a time. It doesn't seem like a lot, which is good, because from a farmer's perspective, it's a pretty simple system, put it on my farm. But if you get all the farms doing it, there's over 200,000 farms in Canada alone. If you had all the farms doing that, then it really adds up. Next, we show another chart here depicts the carbon credit revenue. So that's something that's becoming very interesting in the world, is a carbon credit revenue. This in Canada alone, over the next 30 years from these systems, in 30 years, each system will generate $816,000 in Canada, higher in Europe. So carbon credits are priced depending on where you are. And in Canada, if you're a farmer, if you look at, well, why would I buy this? The system itself costs $950,000. And in a 30-year period, based on today's projections of carbon credits, you'd be at about $816,000 in revenue. Carbon credits are, they're poised to go up even more. Basically, if people don't follow the plan, they're going to start putting more pressure on people on companies by applying more carbon taxes. So those carbon credits are, we would expect them that they could probably go up unless everybody got on board, including China, Russia, India, and we saw substantial gains that saw us reduce our emissions by 2030, maybe by an additional 25%. Then you could probably start reducing that, or I wouldn't say reducing, but maybe stop increasing it. Our system itself, this is our specs on our system. Let's look at some key items. So 300 kilograms per day. How much water does it use? Because we're using water. So water is an important resource. It uses 504 liters per day, but what's 504 liters? So if we look up how much usage a normal average household uses. Now our information comes from houses in Toronto. So I don't know if houses in Toronto use more water than any other house, but a house in Toronto uses more than 504 liters a day on an average household. So that gives you an idea how much water it uses. So the distributed system, so let's just understand what we mean when we say a distributed system. A normal system today is made in these big refineries in one location, and they're using natural gas to heat up water to create steam, and then they create methane, and they pull ammonia from it. It's using fossil fuels, creating lots of GHGs. It's all in one location. If a company says, okay, we're going to get on board and we're going to convert that into an electrolyzer, and we're going to make green ammonia, they need water. And in general, if you look at our system, 300 kilograms of ammonia is roughly 500 liters of ammonia. It's not quite there, but it's roughly. So roughly 1 liter of water for every liter of ammonia. So if a company, and I won't name off any names, because although they're doing a lot of good by converting over, but just imagine if they set up just outside of Waterloo and started drawing off our water table for that. I would be concerned. I would like to see a plan and a strategy of how you're dealing with that. What some of the companies, they recognize this. So one company in particular is building their new plants on the banks of the Mississippi River, and they're going to draw off the river for the water because they realize that there's a significant impact on the water supply. So what do we do with that water? If you're in Manitoba, the water tables are extremely brackish, then you have to purify the water. If you're purifying that kind of water, you're probably going to use 3 to 4 liters to create every liter of purified water. So now you're using more water. So what our system, because it's distributed, it's only on that farm, so it minimizes the impact on the water supply. In Manitoba, they don't take off the well, they take it off the municipal system, and there's no permits required because it uses so little water. Electrical consumption. So I want to really touch on this. So when we look at the consumption of the electricity, it's 500 kilowatts is our pilot system. Now our pilot system is built like a supercharged transformer. Like if you were to watch DC Comics or any of these movies, you'd see this pilot system. The next system would be like sequel number 3, would be very boring and very, very small, and there's not much to it. So what we do is we take that first system, and if you have a pipe train in our PNID, and we've got one valve on the commercialized system with no sensors in that particular section. On our pilot, we'll have 2 or 3 sensors. We'll monitor the heat, the composition, we'll monitor the pressure. They're all very expensive and they take power. If we're wanting to have the ability to produce 150 bar of pressure on the pilot system, we want to be able to produce 400 bar of pressure. Because when we start developing new catalysts or we want to check the optimization of the system, we're going to want to run some tests. So what do we start with? We ask our chemical engineer, what do you want to start with? So, let's start with 200 bar and let's start with 300 degrees C. And let's see what happens. So we know from our modeling what that should do and we validate that. Now let's see what happens if we start to drop it. We drop it down to 200 bar and we go to 300 degrees C. And we start validating that, hey, this is looking okay. Let's drop it again. We drop it again, and now it's going the other way. But what happens if we pump up the pressure and pump up the heat? What if we start increasing our conversion rates by 40% when we've only increased our pressure and our energy by 10%? So that might be a good thing to do. But we won't know that until we actually do it. We have our models and what we want to test. So we've built this system that we can use it as a development system. So it does take a lot more power. This is also at full load amps. So this is using turn everything on at once and leave it on. It'll use 500 watts. You never do that, right? If you do that, you're pretty silly. But we have to have the ability to do that when we size it. Steady state power consumption, we're expecting it roughly to be 350 kilowatts. But when we go into the commercial versions, we're looking at a full load amps of 250 kilowatts and 220 kilowatts of steady state power. And our target system where we think we're going to be able to get to is roughly 150 kilowatts. And that's without any significant development in the electrolyzers or significant development in the catalyst. That's strictly mechanical engineering of the system and take this out, make this smaller, bring this closer, recycle some of the heat because you're creating heat for the gases, but then you want to remove the heat after the gases so you can separate the ammonia. Well, that heat that you just removed, you can put it back in and recycle that and preheat the gases. And the electrolyzer runs a little bit better if you're heating up some of the water and et cetera, et cetera. So as you start to look at where you can optimize, then that starts to change. There's another spec sheet of the length of the first system and width, not that important. Safety certifications are important, but you just have to trust me on that. It's extremely safe. And we have a government, fortunately, we have a government and several different bodies that make sure that it's safe. Everything gets tested. So here's a picture of our electrolyzer in Waterloo. So what we've got, here you see the picture of the electrolyzer Waterloo. Again, some more bullet points that we can skip over some of them. The one I want to point out is the aqua ammonia modules coming later in 2023. Why that's so important is because in Ontario, for example, the regulations are so strict around anhydrous ammonia. So if we look at the customers, we don't want to force a customer to switch to anhydrous ammonia because it takes a lot of training. You have to be very comfortable with it. And Ontario is very heavily populated. Just one of the standards for anhydrous ammonia is you have to be so many kilometers away from any village. So in Ontario, if you looked at KW, where could you put an anhydrous ammonia tank? It would be difficult to find a location where we are. Like, are you going to put it in St. Jacobs? Well, you're pretty close to a village. It becomes very difficult for that. So aqueous would make sense. Also in Europe, they're really pushing for the aqueous ammonia. They know they need it, and there's not a whole lot of anhydrous use there. In the prairie provinces and the Corn Belt, it's used to an extreme, but they really know what they're doing. A little bit more on the base system specs, but we're going to skip over to the solar array. So if we go to run one of these systems on a solar array and take it completely off grid, what we'd need is a 1 megawatt solar array. But as we know from solar arrays, the technology is advancing fairly quickly. It halves in cost and doubles in output. So that's going in the right direction. But currently, if you were to buy a solar farm right now, for this first farm that would use the 300 kilograms per day, we show a grid there up in green. That grid represents 1 acre, 1,800 acres, an 1,800 acre farm, which is the farm that we're going to put our first system on. They're going to use it on an 1,800 acre parcel. They actually have about 8 or 9,000 acres, I believe. But if you're going to use a solar array on that, it would only occupy 1.5 acres shown in those red squares, roughly just over the size of a football field. Here you see some more interesting photos. This is in Waterloo. This is our system in Waterloo. On the left, you see the electrolyzer, and there's a chiller. We're removing some of the heat that's required. But then we're going to be recapturing that heat. When you're building a system from scratch, you want to get to making your product first, and you start finding some opportunities to improve. And that's definitely an opportunity to improve. But this is located right there in Waterloo, the electrolyzer. You can see it started with a SolidWorks design on the top right, a little bit more detail inside those little cartoon boxes that we can't show you. We have a compressor, very safe compressor, but it compresses the hydrogen. And we have a new technology, some new technologies coming in the compression area. And we've completed some commissioning. We've completed what's called FAT there, factory acceptance testing. So it has run at rate, and we've validated the purity. We are now commissioning it with the whole integrated system. This here is our nitrogen generator. It's completed and being commissioned right now. It's again started with a design. And there you see, actually the top right is inside the plant. You see the nitrogen generator inside. We can safely create nitrogen inside. There's some nitrogen buffer bottles. There's also a chiller in front of that. You see inside, the bottom right, you see the instrumentation panel where we can monitor pressures. Some of those gauges that you see there, they're just for immediate viewing when you're inside for something to look at. Everything is monitored through the software system. And we can monitor it from here. When we deliver it to Manitoba, everything's monitored. There's about 1,200 I/O. I/O is inputs and outputs. So about 800 in, and there's some analog outputs, and there's digital outputs as well. But we're generally monitoring over 140 key points, including composition of the gases. So it's It's quite the system. Here's the design bottom right of the ammonia synthesis plant. So this is a plant that converts the hydrogen and nitrogen into ammonia, designed there on the right. It will end up in that container on the top right, and on the bottom left, you see the system as it progresses being built. It's almost finished being built. One of the things to remember, why is our system, you might think, well, why is the system so special? It is smaller, and from a scaled down version, you can put this right onto your farm. So just imagine if you needed fuel for your vehicle and you could just make the fuel right at your house. From a farmer's perspective, fertilizer is the #1 input that they spend on. Some farmers spend millions every year on fertilizer. So if they can make their own there, it's very significant improvement. If you're a farmer, let's say you're in Manitoba and it's getting close to the beginning of April and you think, I want to plant and I want to fertilize at the same time, I'm going to call my supplier for my fertilizer, and the fertilizer says, sorry, Joe, Bill down the road bought all of my supply of fertilizer. And that's actually happening, and they can't get the fertilizer. So now they have to pre-order the fertilizer. And sometimes they can't even get the pre-ordered fertilizer. Also with weather, if I decide I'm going to apply this weekend because the weather is really great, I call my supplier and they say, well, sorry, everybody else booked. I can't get it to you for a week and a half. And now you wait and it's cold and wet and dreary. And if you apply when it's raining, you might get some leaching into the water table and into streams and creeks. So what this does is it allows the farmer to satisfy one of the 4 R's. So in farming, I don't know if you've ever heard of this thing called the 4R program. It's the right source, which is the right kind of fertilizer for the right plant at the right time and the right location. So using the 4R practice, farmers have adopted this in Canada, and they're pretty diligent about it. And if they use the right fertilizer for the right plant at the right time, they minimize a lot of the nitrogen emissions. So it's really important that we give them the tools that they need to work with. So this does help with one of those tools. Here's some more pictures here. Let's see, on the right, we have our ammonia separator. That's a custom design. The ammonia separation rates are very high. So which means that we're pulling, when you make ammonia with nitrogen and hydrogen, not all of it gets converted. So what do you do with the stuff that hasn't been converted? You recycle it through and you run it through again and you convert it. So you don't waste it. It goes back through until it all converts into ammonia. But at the same time, if you don't pull all the ammonia out, the recycled gas contains some ammonia. So the more space you take up in your converters with already converted ammonia is a waste. It's very inefficient. So if you can pull as much from your separator, so we've got a special IP on the separator. In the middle, you see our ammonia converter. You've heard me say converter a lot. You might, well, isn't it a reactor? Well, when our people cross the border and the Border Patrol asks, what do you guys do? We say, well, we design fertilizer reactors. They look at you really funny and they always ask you to go to secondary. So when we say we're making fertilizer converters, oh, okay, whatever that is, and they kind of let you through. So we like to call them conversion units. So there you see in the middle our IP, that's one of them. And in each container, there's 5 of these. So you can imagine later you'll see, and Claudia, please keep an eye on my time. Okay, so because I want to get to that case study. In the case study, you'll see a completely off-grid machine, and people ask us this all the time, is how do you deal with fluctuations of power if you're off-grid? If you're in a rural community and they've got solar and wind, and at night they don't have solar and they have very little wind, what do you do? Like in a traditional system, you can't shut it off. You shut it off, it takes months to shut it off. It gets dangerous. You get thermal runaway on your converters. And so what we did is we said, well, let's mitigate some of that risk, increase the ability to control by making them smaller. A large portion of the cost is the control head. Like if you look at a PLC, it's the main PLC rack and everything that you need for that. If you already have that, as you scale up, you're just adding some I/O modules, which are very cost effective. So then what we do is we split up that unit up to 5 controllable units, and it's not very difficult to start to take down one unit. So if you can imagine you've got a converter and you've got it hot and you've pressurized it and you're creating ammonia and you want to shut it off. You don't just flip a switch and shut it off. There's catalyst in there. You can start to get some runaways. So what we do is we can accurately and efficiently control that temperature by cooling it or heating it whenever we want. Because it's such a small amount, we can control it very, very quickly. But we can stop it from producing ammonia by starting to cut off the supply of hydrogen. So choke off the hydrogen fairly quickly to that converter and just supply nitrogen to it without changing those temperature and flow and pressure parameters, which generally might cause some instability. So we start removing the hydrogen. And so I'm not a chemist, by the way, but I'm just remember what Francisco told me. But my expertise comes around the control and the mechanical design. So I believe we can control pretty much anything if we know what we're dealing with. So we've already have models around the catalyst. We want to develop further catalysts, so we will have a few of these converters in our lab to work with, and we will have some smaller versions of them even. And we're hoping to get some of the research projects with University of Waterloo. Okay, so we're gonna start bumping up the speed on the slides here. How much time do I have? 5 minutes. Okay, so sure. Okay, this talks about the ammonia supply chain. The anhydrous ammonia supply chain is down there at the bottom. You see the blue is ammonia. And the actual anhydrous is the thinnest line that you see going down for agriculture. So this is where it's headed. So the farmers are getting choked off of their supply. We're going to talk about some of the different leads, but here's our customers in Manitoba that are going to take the very first system. And again, I want to get to the case study. But this shows their farm. It's a significantly sized farm. All that land that you can, almost as far as the eye can see. Manitoba is very flat. If your dog runs away, you can watch him run away for 2 weeks. But almost all of that land is theirs, and they will be putting the system just outside of there in Sperling, Manitoba. There's the design of the system. The first system contains an office. It contains a portable lab and some separated controls. So it is a little bit bigger. Now let's get to the case study. So the full off-grid system, we do work with an advisor, an Indigenous Clean Energy advisor, Daryl Brown, and he is identifying some remote communities that we can work with. But we hope to get a system completely off-grid somewhere else where it's very economically viable. And we have already identified that solution. And this is the model that we see with the power. Referring to the chart, you can see the example of the production. In the gray, we have our available solar energy. The colors probably should have been a little different, but in the gray, we have the solar energy that's being produced. You can see the red line is the charging threshold. The red line is the 500 kilowatts that our system would use at full load. And the yellow is the available wind energy. And the energy consumption from the system is the blue. So the energy consumption basically follows the available power. And then once you get above the charging threshold, we start to charge the batteries because they do have some battery storage at this location. And the brown color there that you see is the power that we get back from the battery. So under that red line is where we start drawing the power to extend our production on our system. So in this particular system, the production loss is somewhere between midnight and 6 a.m. So we go from roughly a 12.5 kilograms production per hour to roughly 10 kilograms of production. So now this is taken from capturing the data from November. And then when we look at, so some of the bullet points, solar and wind energy, solar is 630 kilowatts plus wind at 500. Full capacity is assuming 500. We know we're below that. But then now let's look at this slide. But now it's showing the production of our system, and you can see the line at the top, how it goes all the way up top to, and if we go to the right, on the right axis, you see it's 12.5 kilograms per hour that it's putting out. So you see that we actually lose production in between. So that's where it becomes very important with our system that we're able to turn down the system and minimize the production of the system when we're dealing with these intermittent power supply systems in rural communities or off-grid applications. Now, we can easily solve this by adding more solar, by working with them and say, okay, well, let's add enough solar to keep your production 100%. For this particular application, nighttime power is very cheap. So in Ontario, if you turn on power right now, you're probably paying 12 cents per kilowatt hour. At night, you're probably down at 6 cents. I'd rather pay 6 cents than 12 cents. So at nighttime, if we change and run 100% power at the cheaper rate, and we go back on grid at nighttime, that starts to solve some of our problems. Right? So maybe you don't need to increase the solar, you just go off grid. And now finally, this last slide here, assuming continuation from the previous month. So this is a year-long model. So you see some residual power coming from, or residual deficit actually from the month before, from June. And then what we see is we end up with full production on day 3. So what's the difference here is this is July. So there's more daylight and more daylight hours. So in July, if you see after day 3, our system doesn't stop producing. So this is completely off grid and the system just keeps on running. So we believe that we're addressing, now we don't have all the answers solved yet for completely off-grid solutions that could be utilized in remote communities. Remote communities could mean pretty much anything. It could be just outside of Elmira, or it could be in the Northern Territories. But we do have to have some data from the solar and wind power, and then we can actually custom create a solution. So that's it for the presentation. How was I for timing? That wasn't too bad.
Just about on time. Thank you. This one? Okay. Thank you very much, Nelson. So we have a few minutes, another 10 minutes or so for questions. So any questions from the audience? Thank you. Go ahead.
So I'm very curious about the control. Okay. Thank you. So when you talk about the case study that you have, right? So you shut down the plants at around midnight, but then there's always a bump up at around 3 p.m., right? If you look at that graph, I was wondering why you allow that instead of just shutting it down entire night.
So there's a control process involved, like a sequence of operations. And what we want to do is get that down to a predicted minimum as quickly as possible. And then we go back and we look at what's left and available for us. It's kind of like coming home at night and you got really hungry, you open up the fridge. If you just start taking everything out of the fridge and you got nothing left for the morning. So you kind of predict, I might be hungry in the morning, so I'm going to leave that for the morning. So what you do is you start bringing it down where it's safe, and you can predict what you can do in that time frame. And then once you're done, you see how much power you got available that remains, and you can say, okay, I can squeak out a little bit more production without turning off my nitrogen flow within those converters, and I can continue my nitrogen flow, because it's all about safety at that stage and making sure that you can power up and ramp up fairly, well, not fairly quickly, but you want to ramp up as power is available. So you want to maximize your production output in comparison to your power availability. So does that explain?
Yeah,
why that's there.
Thank you.
Thank you. Follow up with that. Is this an actual installation or is these are sort of simulations?
That's going to be an actual installation. So those are actual numbers coming from an actual solar grid, an actual wind farm that our system will be supplying green ammonia for.
So these are the electrical characteristics, and then you're on top of that, you are in your systems, see how it would work.
Correct. So they've provided us the data, and we provided the production output so that they can decide should they increase their solar farm or their wind. In this case, I don't think they're going to do that because it's.
Where is this located? Sorry,
I can't tell you exactly.
Oh. You have to kill
because
me.
we're a public company and we haven't announced it yet.
Okay.
So we still have to formally announce it.
All right. Thank you. Any other questions? Yes.
Thank you for a great presentation. I just wanted to ask if you can share what would be the overall efficiency which your system is having right now based on this green ammonia production. Start from the impure water.
So impure water right now, the water is actually a pretty good supply, but we have a water purification system, but it doesn't require a lot of purifying in the water, so that's fairly minimal. But if we look at what we're looking at overall system efficiency numbers, we're probably, and I'm going to take a guess here, probably in around 60 to 70%. A lot of that has to do with the electrolyzer. So when we look at what of our obstacles or our challenges moving forward, our system is the ammonia generator. So if you said to me, hey, I've got an electrolyzer, do you want to use it? I would say, sure, let's just plug in. Now you're going to pay a lot less for your system. The electrolyzer is responsible for approximately 65 to 70% of the CapEx. So that's a really expensive portion of it. And the electrolyzer technology, we're trying two different technologies here, alkaline and anion exchange. The anion exchange is much more efficient. So if that's successful, it's a newer technology. If it is successful and we can switch over to anion exchange for future systems, then the efficiency on the electrolyzer alone, I think it goes up by about 35% just on the electrolyzer. So just imagine, so we're really excited, and if it works out, then just a matter of keeping that CapEx down for future systems.
I have a question about the use of.
He might have another. You're good?
Okay. I have a question regarding the use of ammonia as a fuel. And one of the challenges with using electrical or batteries for heavy transportation, as you mentioned, aviation and shipping, right, is that batteries don't really work. So you're talking about hydrogen, but you mentioned the use of ammonia. Could you elaborate on that? How would that work and what the emissions would be on that?
Sure. I don't have specifics around exact emissions. A lot of these are new projects, so they're very secretive, but what they are telling us is there's two styles. So one is using ammonia as a fuel cell. So you're cracking the ammonia back to hydrogen, and you're basically using a hydrogen fuel cell. So the ammonia is basically a carrier, then you're cracking it back. It sounds a little silly because you're putting all this effort into making ammonia, then you're putting effort into cracking it back. And then other companies are burning the ammonia, but they're controlling the NOx emissions currently with standard emissions control, so catalytic converters and that sort of thing. So they're capturing the exhaust and removing the emissions. But the problem with that is the supply of the materials used in the catalytic process for capturing those emissions. A lot of these companies say that they have it solved. So we're hoping that they do, because if you look at that chart showing the maritime, maritime consumption is going to be huge, like to an extreme. So,
thank you. A question for another time for another question or so.
From your ammonia generator or reactor, look like it's a homogeneous phase reaction, and it may involve heat as well. will you be interested in considering something like electrochemical synthesis, which will make the system much simpler for ammonia synthesis?
We're interested in trying anything, right? We're an evolving company, and we have some institutions working on some research. There's some very interesting research being done in Cambridge University, where they produce the ammonia without the electrolysis. But that's at lab scale, and we've seen electrochemical. But when we start to deploy it in a model, in an industrial model, and we look at how much it costs to make. So if you look at that ammonia plant, just imagine what we had to do to build this plant. So I've been with the company not even a year and a half. When I came in, there was 3 people, there was no location, and then we had to build an ammonia building factory. So we had to build it safely. No, knock on wood, we haven't had any accidents. And we're making hydrogen and we're making ammonia. So we had to build this factory out very, very quickly, and maintaining all safe practices, train everybody on ammonia safe practices, hydrogen, compressed gas safety. Some of the designers have never worked with gases at that pressure. I'm fortunate, I worked from the water jet industry, so we were running at about 90,000 PSI, not 2,400 PSI. So I'm very familiar with high pressures, but not as familiar with ammonia. So that's why we have to bring in the experts, and then we work as a team to build up what we're doing. So when we started evaluating some of these processes, we look at what it's going to cost to turn that into a commercialized piece of equipment, and where will we get all the raw materials? Are they readily available? So if we start selling, like an example is here, when we're going through some of the sales numbers, we're talking hundreds of systems just in the first year that we could sell. But how do you make 100? Like, how do you make 30 systems we could sell in the pre-orders, like, without any issues? But how do I get 30 electrolyzers? It was pretty hard just to get one. And so we have to look at, we're going to have to make these. So if we look at your process, that process, and we see that it simplifies things, and if we can start making everything here, then we would definitely look at it. So I'm very interested in any of the new technologies. There's another technology that Jiawoo has been working on that we're extremely interested in. I can't show my excitement because then he's got leverage.
Very well. So, yeah, time for one last question.
Two questions, very quick. First, any limitation in terms of the temperature or the weather, if there is a range of temperatures that this would be working, if there is any limit for hot temperatures and also very, very cold. And also, who is your supplier for, as you said, it can be difficult nowadays to get the electrolyzers, the orders. So I'm wondering if what plans you have and what are the suppliers that you have been using?
So currently, I can't name off the exact suppliers, but the suppliers of electrolyzers, we worked with a supplier in Italy for our first one. They produced a standard electrolyzer, and then we worked with them to I wouldn't say improve, but modify their design to work with what we're trying to do. We need access to be able to optimize certain aspects of their system and then build onto that system. So they've built a system that's a dual stack. They sell systems that are single stack, so that we could possibly increase the stack and keep one running, because we're in a commercial environment, so we can't stop producing ammonia for the farmer. So if we want to manipulate one stack, we can take that stack down and work on the other stack, and keep producing on the other stack while we're working on that stack. So we had to find a supplier that was willing to work with us on that. We did find a supplier like that, but that's alkaline, so not long-term solution as we see it. There's some PEM suppliers that we're working with, and then there's an anion exchange membrane supplier. That supplier has been very good. They're in a growth stage right now as well. So we ordered our first unit from them, and they weren't even making units yet. So we actually had to take one of their test units, and we'd like to work very, very quickly. So we had to convince them, they just give us your test unit, and then they had to rebuild another test unit. So we have that unit in Waterloo. We've ordered seven more units, which we're going to take in about 2 weeks. And they're able to produce us enough to make about 10 systems, but not to make 30. So yes, that's definitely an issue, is supply of the electrolyzers. So we are looking for other, we're working with some other companies as well. Now, the answer about the question about the temperature. So right now, the first system's going to Manitoba. So you don't worry too much about heat in Manitoba. It does get hot, but it's not like a desert. So in Manitoba, I believe we're capable of running up to 110 degrees Fahrenheit. And we're able to go to, it's funny how people talk about heat in Fahrenheit, but cold in Celsius, right? That's what we always get. In cold, it goes to minus 45 degrees Celsius. So I think in Manitoba, they haven't seen anything below 42, minus 42 in something like 50 years. So it's all climatized, but that is an issue. So when we're quoting scenarios, we have to look at case by case. Well, where are you? If you're in Manitoba, we have to provide heat for the system. But we see that as an opportunity to recycle the heat that we're pulling out from the gases. So an example is on the one picture, there's a heater on the floor. We're hoping we never have to turn on that heater, because if we optimize our system properly, we can recapture some of the heat that we have to pull out and use it within the container to keep the system warm. So it does pose a problem in some areas, so but we do have to consider it.
Well, thank you very much, Nelson. I appreciate it. Thank you again.
Yeah, thank you for having me. Appreciate it.
Thank you for a wonderful presentation.